maybe? Yes. Okay, and we will go ahead and get started with today's lesson. I'm sure there's going to be a couple of stragglers coming in. I wanted to do a couple, one example off of what we did yesterday to start off today, kind of like a warm up or bell work, and then we'll kind of finish up where we were yesterday. So, if a person were to throw a ball up and it kind of followed this trajectory, okay, and I looked at different points, or I looked at the speed horizontally and vertically after 1 second. Might be there, there, there. And again, this is not, there's no wind resistance here, no air resistance. We're going to talk about that in a minute. Okay, so this is the 1 second mark. This is 2 seconds, 3 seconds, so on and so forth. Okay, now let's assume that this person threw this object with an initial vertical component 30 meters per second and an initial horizontal component of 5 meters. Okay, so how would we figure out the actual speed at which this person threw this object initially? You can chat, or you can unmute yourself if you happen to have or you can write on the screen. It'll say who you are. But how do we know what this is? Anybody have any ideas?
Well, you just take like the resultant vector, like do a squared plus b squared.
Exactly. So we would take 30 squared plus 5 squared, and what would that be? 925. So whatever the square root of 925 is, probably about 30 point, I'm sorry, yeah, 30, we'll just say 30.1. Okay, but if you look at the angle, he almost threw it straight up. Okay, all right, now let's go to the first second. Who knows how fast this first second, now what is the vertical component of the velocity of that object after 1 second? Anybody want to venture a guess? Because the initial velocity was a vertical component of the velocity was 30 meters per second. So what is it after 1 second? Okay, so I will call on somebody. Who shall I call on? I am going to call on, oh wait, Michelle has an answer, I think. 20 meters per second, that is correct, Michelle. Because it's slowing down 10 meters per second every second. Okay, so after the first second, it's 20 meters per second. What's the velocity after 2 seconds? Sorry, that should be a little bit longer. Okay, that would be, yes, 10 meters per second. Okay, now how about the horizontal component of velocity? Right here, it started off at 5 meters per second. So what's it going to be at this point? I will call on Megan.
Is it 3 meters per second?
Well, it was 5 here, right?
Yeah.
Is there anything slowing it down in the horizontal? Is there any gravity affecting the horizontal?
Oh, no.
So what would it be?
So just be 5.
5 meters per second here. And then right here,
5.
and 5 meters per second. And we could fill this out the whole way down, right? It'd be 5 meters per second everywhere. All right, thank you, Megan. Now, obviously, I hope it's obvious that at the peak of its parabolic arc here, the vertical component of the velocity is 0. Okay. How about the 4-second mark? What is the vertical component of the velocity going to be at the 4-second mark? Okay. Let's see if Maddie knows. Maddie, you're on.
Is it negative 10 meters per second?
It is negative 10 meters per second. Okay, this is still 5. Okay. Did you quickly unmute yourself, Maddie?
What?
Oh, I was just seeing if you unmuted yourself or not. Okay. Or if you muted yourself. That's okay. Now, let's do this for this last one. What would be the resultant speed at the 5-second mark? What would be the resultant speed at the 5-second mark? Okay, because we know this is going to be 5 meters per second. This now is going to be negative 20 meters per second. So what is the resultant vector? Anybody know what the square root of 425 is?
It's like 20.6.
20.6 sounds about right. So that'd be 20.6 meters per second would be the resultant vector. Okay. Now, down here at the bottom on our last thing, that's supposed to be longer, but I ran out of space. Okay. What will the resultant vector be at the bottom? Should not have to calculate that. Let's ask Skyla. You're on, Skyla.
What is the resultant factor of that? I don't know, 0?
What's this? This right here.
But how can it go more down if it's hit the ground?
Well, we're saying just hits the ground, smarty pants.
Oh, sorry.
You're muted now for that. So 30 so whatever the initial velocity was, the ending velocity just before it hits the ground would have to be the same. Okay. Now, all of these calculations that we're looking at are obviously without any wind resistance or air resistance. Okay. I shouldn't say wind, I should say air. Okay. But hopefully we understand this a little bit better now. This is from earlier chapters that the velocity is either going to be sped up by 10 meters per second if it's going down, or it's going to be slowed down by 10 meters per second if it's trying to go up. Okay. Anybody have any questions on this particular problem before I get rid of it? All right, then let's talk about this next. If we have a projectile that makes that arc, in reality, if that's a soccer ball or that's a golf ball or that's a baseball or we're throwing it even, is that really what the path looks like? Probably not. it probably in reality looks something like this. It probably starts off, and then this side should be a little bit steeper than the original side, okay? Why is that? Why is the actual less than what I'll call the theoretical?
Is it because wind resistance changes the horizontal component?
Exactly why. Air resistance, it only affects the horizontal, but that's going to change the distance by whatever that amount is, right? Now, if you have a ball that spins, like a soccer ball, golf ball, baseball, the second half of this fall could be even steeper than what I have drawn here. But I just want us to make sure we understand that in actuality, the path is going to be a little different than what we're drawing here. We're kind of talking in a theoretical sense, okay? So, next thing, let's say that this is the Earth. That's not very good. I'm gonna try that again. Yeah, it's a little better. Okay. Let's say that we were going to launch something. Okay, we're going to throw something horizontally, and we're up here at the top. Okay, and we launch something horizontally. Okay, how far will that object fall in the first second? Carissa?
5 meters.
5 meters, that's correct. No matter how hard we throw it, it is going to fall 5 meters in the first second because horizontal and vertical velocities are independent of each other. Now, it could fall that 5 meters right there. Okay, that could be 5 meter mark. Okay, let's try a different color. If we throw it a little harder, it might fall 5 meters right there. If we throw it a little harder, it might hit there, right? And what I'm getting at is if we throw this object hard enough, what's going to happen? I need another color. Let's go with pink. What's going to happen is that the curvature of that object will match eventually the curvature of the Earth if we throw the object fast enough. Okay? But no matter what, in the first second, it is going to fall 5 meters. Okay? So, this is how we start to talk about satellite motion. Okay? So that's why we said in an earlier chapter, a satellite is something that falls around the Earth instead of falling into the Earth. All of these other points right here would eventually fall into the Earth if we kept them going on their trajectory. Okay, they would hit the Earth at some point. But that pink line, or maybe it's fuchsia, I'm not sure. That line there will, if it's going fast enough, it will match the curvature of the Earth. Now, why is speed important? We just kind of talked about it in the previous example. Why is the speed what affects whether or not something goes into orbit or not? Let's see, Addie. Do you know the answer to that, Addie?
No.
what does speed, that the speed at which we throw that ball, let's say, what is it really only affecting?
I have no clue.
Let's see if Jenny can help you. Jenny, you got any ideas on that?
I don't know.
We said in the last example that the reason that an object would fall shorter is because of air resistance. And air resistance only affects horizontal velocity. So we have to throw this hard enough horizontally for it to fall at that same curve. Okay. Now, it's not really possible for us to throw something fast enough to cause it to orbit the Earth. But I want to make sure you guys understand that each of these little marks right here, it's going to fall 5 meters and eventually hit the Earth if that curve isn't matched. Now, the speed, velocity that is required in order to match this curvature of the Earth is 8,000 meters per second. So anything less than 8,000 meters per second and it falls into the Earth, right? Which way is gravity pulling on this object right here at this point? Gravity is only pulling that thing that way. Gravity is not slowing this thing down. The only thing slowing it down is air resistance, right? So, because gravity only works in this way, the velocity is working in that direction. And this is what we said a couple chapters ago, right? Like if we were spinning something on a rope on a string and we cut the string, what direction would it go? Well, it'd go perpendicular to the radius, right? It would continue in a straight line if we were to cut that string. Well, in this case, that string is gravity, okay? Now, I use the example of 5 meters here, but really we cannot throw something fast enough if we're only 5 meters above the Earth, which is like 15 feet. We can't throw anything fast enough to reach 8,000 meters per second, or if we do, it will slow down. Why? Why would we, if we could throw something 8,000 meters per second, why would it still fall into the Earth instead of orbit the Earth? Anybody got any ideas? Paige really wants to answer.
Well, like, do you mean if you're standing on the surface of the Earth and you were throwing it? Or I don't know.
Anybody else have an idea why it would not continue to orbit the Earth if we threw it from the surface of the Earth? Even if we threw it at 8,000 meters per second?
Is it because it would eventually hit a mountain?
Good thought, but we'll pretend there's no mountains right now. There's another, what's the right word, realistic reason for it, other than a mountain, but that's a good thought. Let's say we're standing on a mountain. We're standing on Mount Everest. How about that? We're standing on Mount Everest. We throw this thing horizontally at 8,000 meters per second, or we launch it. Why will it still not orbit the Earth? It will eventually fall into the Earth.
Because once you let it go, it's in free fall and speed doesn't affect the force of gravity.
Right, but yet it's still gonna. But at some point, it's still right. That's exactly right. But at some point, it's going to slow down, and it's good. And once it slows down to less than 8,000 meters per second, it's going to curve into the Earth eventually.
Is it because it's still in Earth's atmosphere, so there's still like stuff hitting it and slowing it down?
Air resistance. air resistance will slow it down to where it's less than 8,000 meters per second. This is why we don't launch satellites from the surface of the Earth, right? We take them up into space and we get above the atmosphere. And then when we launch it at 8,000 meters per second, then it can stay in orbit around as it's falling around the Earth, right? So just to get it, kind of give you a simplified picture of that, right? If this is the Earth, what we do is we launch a rocket up kind of a little bit at an angle, and once it gets above the atmosphere, then we launch that satellite or whatever at 8,000 meters per second, okay? And it will orbit, it will stay in that orbit because now there's no air resistance to slow down the horizontal velocity, right? We have to keep that horizontal velocity at 8,000 meters per second. Vertical velocity doesn't matter at all, okay? So the horizontal velocity has to stay at 8,000 meters per second. Now, there's a chance even out in space, it could slow down just a hair. And that's why they monitor satellites and might give it just a little bit of a boost every now and then to make sure it's staying above that 8,000 meters per second, okay? But it has to be above the atmosphere in order for it to do that, because if it slows down at all, it's going to go into the Earth. Have any of you seen the movie Gravity? It's a movie with Sandra Bullock, and she kind of gets stuck out in space. But there's a scene where space trash comes flying by her little capsule, and it is hauling butt, and that's very realistic. Those satellites that we think are not moving very fast, they are flying at 8,000 meters per second, or even higher, depending on how things are. Now, why does it have to fly at 8,000 meters per second? Well, because that is the amount of speed necessary to escape, or not to escape, but to match the gravity, the force of gravity of the Earth, okay? If you happen to launch that object higher in the atmosphere, higher into space, it actually can be less than 8,000 meters per second. It's still got to be pretty fast, but it can be less than that the farther you get. The moon does not travel 8,000 meters per second around the Earth. It's going slower because it has a bigger radius. So Earth's gravity is not pulling on it with the same force. Okay. All right. One kind of cool thing about this is Isaac Newton understood this, and he could calculate all this. It just never occurred to him in a million years that we'd be able to create a multi-stage rocket that would allow us to get above the atmosphere, and be able to attain that 8,000 kilometers per second. By the way, in order to get out of our atmosphere, you have to go about 200 meters above the surface of the Earth. Okay. Now, interesting enough, 200 meters above the surface of the Earth, the force of gravity is not that much different. Okay, so don't think that something that a satellite orbits the Earth out in space because there's no gravity. There is gravity, and it's almost as strong as it is on Earth. That's why it still has to go 8,000 meters per second. When you see people coming out of the space shuttle and doing their little work out there, they are flying around the Earth at about 8,000 meters per second. Okay. Now, if we were to fire something at 8,000 meters per second, it would make a perfect circle around the Earth. Okay. And just to kind of make sure we understand this, the planets all circle the sun at a certain speed also, right? The farther the planet is away from the sun, the less that speed has to be, which is why, like on Earth, it takes 365 days to go around the sun, but like Mercury goes around it much faster, whereas Mars, it takes longer to get around the sun. But if the tangential speed of the Earth was cut to zero, guess what? The force of gravity between the sun and the Earth would pull the Earth into the sun. Okay, so just kind of keep that in mind. So 8,000 meters per second is the magic number to keep a circular orbit around the Earth. Okay. For something at that 200-kilometer distance above the Earth, it takes about 90 minutes to get around the Earth, to orbit the Earth. Okay, those are the lowest flying satellites that we have. Okay. Communication satellites. Are located about 5.6 Earth radii above the Earth. And they have a period of about 24 hours. And so if something has a period, meaning it takes 24 hours for it to go around the Earth. Well, guess what that means? That means that it does not change locations. It is exactly matching the rotation of the Earth when it is this far away from the Earth. Okay? And as we said earlier, the moon has a period, or how long does it take to go around the Earth, of about 27.3 days. Which is why we see one new moon, one full moon once a month. Okay. All right. Anybody have any questions of what we've talked about so far before we go any farther? Becca, no questions. All right. Then, how do we get then? Okay, let's say that's the Earth. How do we get an object then to go in an elliptical path around the Earth? That's a pretty good picture right there. It looks like an egg, huh? Because most objects in orbit, like the Earth around the sun, or even all the planets around the sun do not follow a perfect circle. They actually follow an elliptical path. So what do you think causes something to have an elliptical path? Any ideas? Oh, who haven't I called on today? Why would something have an elliptical path? Natalie.
Uh, can you hear me?
Yes.
Is it? I thought it was the gravitational pull of the sun.
Yes, but what? But we if the object is going at the perfect speed, it will make a circular path, right? But really, most objects have an elliptical path. Why is that?
I have no idea.
Okay, anybody else?
Is it because I'm just thinking, I don't remember what the movie is called, but where the like space shuttle or something there's something wrong with it and they were running out of oxygen. But anyway, like they used the Earth's gravity to speed it up again or something like that.
You're
So
close.
like because it's closer, then does it gain more speed? So then it like just basically fluctuates speeds throughout its orbit.
Yeah, the movie was Apollo 11. No, I think it was.
Yeah,
And
one
they
of those.
shot it around the moon. Actually, they used the moon's gravitational force.
Oh yeah.
That's exactly right. What that means, if something is an elliptical path, it means that its velocity is greater than 8,000 meters per second. Okay, so let's just kind of review that. If the velocity is less than 8,000 meters per second, it's going to fall into the Earth. If it's exactly 8,000 meters per second, it's going to go in a circular pattern around the Earth. And if it's greater than 8,000 meters per second, then it would follow an elliptical path. At some point, something could go fast enough to just escape Earth's gravity and not return, right? It would just keep going out into space. But we'll talk about that in a little later. But let's kind of talk about this for a second. If the speed is greater than 8,000 meters per second, what that means is it, as it's traveling along here, it's going to want to leave Earth's gravity, right? But it's not going fast enough. So in this section right here, from here to here, the object, the satellite, is actually slowing down. Okay, we're going in this direction here. So it slows down until it gets to this point. And at this point, it's probably going less than 8,000 meters per second. And what happens when it goes less than 8,000 meters per second? It's going to be pulled back into Earth because of the gravitational force. And so now from here, it's going to start speeding up. Okay? Because okay, let me back up a little bit. Remember that Earth's gravitational field is always at 90-degree angles to the surface, right? So when we are moving perpendicular to that, then it's not slowing us down or speeding up, right? But when we start going out over here in this spot right here, you can see that we are now moving against the force of gravity a little bit, okay? Because see, the angle is not 90 degrees anymore, right? This angle is bigger than 90 degrees. So now we are working against gravity, which is why we slow down. Now at this point out here, if we continue this line and this angle now, this angle is less than 90 degrees. So now we are working with Earth's gravity. Okay, and that's why at that point we're going to speed up. Okay, and at some point we get back to that 8,000 meters per second mark again, maybe somewhere in this area right here. We get back into 8,000 meters per second, but guess what? We're still speeding up as we go around. And as a matter of fact, this point right here will be our fastest point, okay, which causes this whole process to repeat itself, okay? So that's why at different times of the year, the Earth is different distances away from the sun, okay? We're actually speeding up and slowing down in our orbit around the sun at different times, okay? But that's kind of a basic description of how things fall in an elliptical path instead of a circular path. The key being, we got to start off over 8,000 meters per second. Okay, questions?
So does it originally begin to slow down because it's trying to leave the Earth's gravitational pull? Like, is that what starts the process? Is that it gets fast enough that it's trying to leave, but it's just not quite fast enough? If that makes any sense?
Yeah, yeah. Like if we wanted to do this, if we wanted something to follow an elliptical path, we might take it right about here, right in this area right here, if we were in space, and we might launch that thing at about 9,000 meters per second, right? Which it's gonna, you know, in theory, it once it gets way over that, it's just gonna keep going, right? But we're now Earth's gravity is gonna slow down because, okay, remember the only thing that can slow us down is the horizontal component. Well, look at this right here, right? That part doesn't really matter, but this part of the components This part right here is working against gravity, right? Gravity is trying to go this way. And this component of this vector is going completely against that. So it's going to slow us down, actually. Okay, any other questions? Megan?
So what like starts it from not being like perfectly elliptical? Like what makes it go faster? What like makes it go slower?
Well,
You know?
that's a great question. Sometimes we can. Like they will calculate, they can calculate, you know, they can say, well, we want this satellite to do this. So we want to launch it at a certain speed because, you know, in pre-calc, I think, maybe algebra 2, remember you guys graphed, you should have graphed ellipses, right? And in an ellipse, there should be 2 foci, right? One is definitely at the center of the planet, but then the other one's here. And so they can calculate how big they want that radius to be. And so they can do that. But like in the terms of the moon or the Earth orbiting the sun, there's no real, we don't really know. Let me draw, oh, hold on. Let me just draw the sun here real quick. So basically what happened is, you know, they think is that the Earth was hurtling through space at a certain speed, and it got close enough to the sun that it just happened to be pulled into an orbit around the sun. But this speed might have been greater than whatever the speed is for the sun, and so it would kind of do this type of thing. It just kept us in that orbit forever, basically.
Okay.
Clear as mud, huh? We just don't know some things. But that's basically how it worked. There are little particles of meteors and asteroids out there that are out there circling the Earth for that very reason. They've gotten close enough, and they happen to be at just the right distance away that as they were coming, just if they're going too fast, you know, they just kind of do this. It just moves on by, right? But if the speed is just right, one of these things gets back into that orbit. Okay. If the speed is too slow, what happens? Right? If the speed is too slow, well, then it falls into the Earth. And what happens as it's falling into the Earth? Well, it's going so fast, and now it encounters air resistance. The friction is so great that it just burns it up, right? So that's why things burn up in our atmosphere, because if they try to go 8,000 meters per second, it disintegrates because of air resistance. Okay, other questions? I know you seniors just want to go get your cap and gown, huh? But I did kind of want this to be a little shorter, so I am going to stop it right here. And